ChatGPT took the world by storm during late 2022, and that kick-started an arms race for generative artificial intelligence. There has been a lot of talk and hype about how disruptive artificial intelligence is going to be and how it is going to change our lives for the better. But how does artificial intelligence work? A while back, I got interested in finding out more about artificial intelligence and machine learning, and so I took an online postgraduate program from GreatLearning University of Texas at Austin, Artificial Intelligence and Machine Learning, Business Applications, to learn more about it. It is a 6-month course and culminated in a capstone project and presentation which I will be going through in this video today. Hopefully this serves as a useful guide or reference for those who are interested in the course or about to embark on their capstone project. So without further ado, let's get started. The problem statement is as follows. Pneumonia is an infection in the lung, which requires review of a chest radiograph by highly trained specialists. Pneumonia shows up in a chest radiograph as an area of opacity. However, diagnosis of it can be complicated and much time and effort is spent by specialists in reviewing them. Chest radiograph is the most commonly performed diagnostic imaging study. Due to the high volume of chest radiography, it is very time-consuming and intensive for the radiologists to review each image manually. As such, an automated solution is ideal to locate the position of inflammation in an image. Having an automated pneumonia screening system would assist physicians to make better clinical decisions or even replace human judgment in this area. This brings us to the objective of the Capstone project, which is to build such an automated pneumonia detection system, by detecting areas of pneumonia in a chest radiograph through using bounding boxes to indicate areas of pneumonia. The project aims to hopefully act as a first-layer check to improve efficiency in diagnosis if the lung was deemed to have pneumonia with the area detected in the picture, and to assist physicians to make better clinical decisions, such as for the images labeled not normal, no lung opacity, to reduce false positives by the algorithm, and potentially detecting other potential health issues which are not pneumonia. Ideally, it would be able to replace human judgment in this process. The approach I took was to first analyze the data and start an iterative building process for building a good neural network as the automated pneumonia detection system. The first model will act as a proof of concept of sorts, and after training the model, it will be analyzed for its performance, and subsequently, minor adjustment tunings to the model features and data inputs will be made and iterate the model to improve the model performance. The model selected for this is a UNet MobileNet architecture. The first version of the model was not very good at predicting the bounding boxes, but analysis and research were done to discover issues and weaknesses of the model, and subsequently the model improved tremendously by the end of the project. Although the model is not perfect in predicting the bounding boxes of areas of pneumonia, it has improved significantly through the iterative process of building the model, analyzing model performance, tuning the model parameters, rinse and repeat. To give a quick summary of the results of the project, with the current stage of the model built at the end of the project, it can function as an automated pneumonia detection system to a limited extent, which is semi-automation. It detects pneumonia with ease but with a certain degree of variance with regards to the precise pneumonia area. Human effort is required to filter out pneumonia-detected images when there is no such pneumonia in the patient. If there is immediate time constraint for model usage, the current model can serve as a first line of defense for screening the DICOM images. After the model predicts the bounding boxes, the healthcare specialist can prioritize patients whose images are predicted with a bigger bounding box area as patients with a higher probability of pneumonia detected. This will alleviate bottlenecks in reviewing such images in their triage process for determining priority of patients to administering the appropriate healthcare service to. Alternatively, if there are no time constraints, the model can be further improved via the following points to achieve better performance and fully automate the pneumonia detection system. Firstly, to improve model inputs to handle a single image with multiple bounding boxes. Second, to modify the architecture of the network via increased complexity to reduce false positives. Lastly, to experiment with different variants of optimizers and monitoring parameters to further fine-tune the model. The first step would be to examine the data available for this and perform exploratory data analysis. The data provided for this are as shown on the screen. To support the building of a neural network, the project will be done on Google Colab. A couple of things to note are as follows. A quick check through the records reveals no missing values. Checking for duplicates, and there appears to be 3,543 duplicate records. The reason is because each row records a single bounding box area of pneumonia detected. However, in a patient image, it might be the case of several bounding boxes of pneumonia detected, such as one box for the left lung and one box for the right lung. This results in duplicate patient IDs, but with unique row values due to the different bounding boxes. As such, since the bounding boxes refer to different areas, the duplicate records are to be included in the training dataset as well. Also, there is a slight imbalance in the proportion of class labels, which may be exacerbated when I proceed to reduce to only having 2 labels, which are lung opacity and the rest. This needs to be addressed when feeding the data into the model for training to prevent bias in the machine learning algorithm. Before proceeding, it would be good to view the image and see how the bounding boxes are like. As such, here are some sample DICOM images loaded from Google Colab, with the relevant labels and bounding boxes where applicable. The top 2 images belong to different patients, while the bottom 2 images belong to the same patient, with different bounding boxes of pneumonia. As a layman, it is not possible to detect a positive pneumonia patient visually unless you are a medically trained expert. This highlights the difficulty in visual inspection of the DICOM images and further strengthens the need for an algorithm to be able to assist the medical specialists in making better informed decisions. Next, I will select a model and start to train it. There are a variety of models available, such as VGGNet, RCNN, and YOLO, but ultimately, I selected the neural network UNet architecture using MobileNet as my model of choice. This is because MobileNet is lightweight, and I considered that there is limited memory available for use in Google Colab. Since there are a large number of images, I needed to be mindful of the memory usage. Hence, I thought that UNet MobileNet architecture would be well suited for this task. Next would be data preprocessing before input into the model. The DICOM images provided are of size 1024 by 1024, which consumes space and memory. In order to work around Google Colab's RAM limitations, I decided to downsize the images to 256 by 256. As a first iteration of a trial model, I used pre-trained ImageNet model weights and froze the upper layers and retained only the final layer for training in order to reduce model training time. I used an ADAM optimizer for the model and selected the metrics shown in the slide to evaluate the model. Due to the limited RAM memory available on Google Colab, I have only loaded 1,000 images, and used the last 5 images as a test set, and 20% of the remaining 995 images for validation dataset. I trained it for 10 epochs, and here are the initial evaluation results. From the results, it seems that the model is performing very poorly. The mean IOU results are less than 50%, which means the model is not really capturing the bounding boxes well. Additionally, there is seemingly no improvement as the model is trained for more epochs. Model accuracy is considered low for both the training dataset and validation dataset. Validation accuracy is slightly higher than the training accuracy and is consistently around the same level across the epochs. For mean squared error, both the training and validation values are at consistent levels. There was a slight dip for the training mean squared error but level off quickly. Lastly, for dice coefficient, since this is a similar metric to IOU, I would expect the results to be similar. However, there is a huge dip for the training dice coefficient and leveled off similarly to the validation dice coefficient. Next, we can visually inspect the bounding box predictions by the model using the 5 test images I have set aside earlier. Below are 3 sample images of the 5 test images. The image on the left has the bounding box predicted by the model, while the image on the right has the actual target bounding box. The evaluation results and visual imaging of predicted bounding boxes indicate that the initial model does poorly at predicting the various bounding boxes. For some reason, the model is consistently identifying possible areas of pneumonia near the bottom of the lungs area along with the right arm of the person for all the images. Out of all the test images picked, it has failed to identify a single bounding box correctly, and even predicts a bounding box when the image does not expect to have pneumonia. The metric evaluation results confirm the visual imaging results through the poor metric evaluation performance as well. There is plenty of room for improvement. For the next iteration of the model, I have thought of some of the points shown on the slide to incorporate into the model building process. After further thought, here are some additional ways of fine-tuning and improving the model. I will be exploring the possibility of trying them out and combining them in iterations to see if model performance can be improved. The first step was to address the main problem I faced after building the first iteration of the model, which was how to train the model on all the training data provided, as Google Colab constantly crashes due to memory issues. Previously I was attempting to load all the files to memory, which due to a lack of memory space, Google Colab will crash. With the assistance of the mentor session and researching online, I picked up on several functions from Keras library which were able to load the files from directory, saving the memory space allowed on Google Colab. I researched further and decided upon creating a custom data generator function which was used to fit the model with data. Subsequently, I discovered an issue where I did not cater for the scenario of a single DICOM image having multiple bounding boxes, and as such, the bounding box masks created overwrites each other with only the final bounding box mask per DICOM image saved. As such, this might potentially introduce some bias into the model due to input impurity. For example, if a DICOM image has two bounding boxes, first being an area in the left lung and the second in the right lung, the bounding box mask that I created will only store the bounding box in the right lung and overwrite the bounding box in the left lung, potentially introducing an inherent bias that it will not be able to detect bounding box in the left lung. This would be considered a potential next step which I will discuss at the end of the presentation. Now, we will begin training the model. Instead of previously only training the final layer, I would now set the model to train all the layers. Next, I would use a small number of epochs to train a few variants of models, and I will train and make small improvements on the decided variant for a higher number of epochs. I have also dropped the performance metric of dice coefficient as it would be a duplicate to IOU. Performance results are shown in this table. It appears that there is not much variance in the metrics across the various optimizers. Additionally, mean IOU was constant across the board. As it would seem strange that the mean IOU is the same, I decided to build a custom IOU function and retrain various models on it. With the newly built IOU function, I decided to train only 3 variants which I believe will give me the best results, taking the lowest learning rate of each of the optimizers, and the results are in the summary table shown. We can see that each of them has a high IOU from the custom build function. This will need to be checked and verified subsequently if the model is indeed having such a high IOU. Since they are generally quite high, I have decided to go with the Adam optimizer for training the final iteration of the model. I would train the model for 20 epochs using the Adam optimizer with a learning rate of 0.001. I have decided to retain the loss function as MSE, as the other metrics that I have selected are not suitable loss functions. Unfortunately, the training of the final iteration of the model did not go as planned. Google Colab crashed midway while running through Epoch 11. Due to a shortage of time, I decided to cut short the training and use the results of the model as of Epoch 10. From the initial glance of the metrics from the 10 epochs training, results seem to be quite good. The custom IOU calculated is quite high, with a low mean squared error. Accuracy may be low, but it might not be a very good metric to assess the model performance. So, here are the graphical results of the final model. From the IOU graph, it appears that the model performance is good. The training IOU is increasing steadily incrementally through the epochs, and the validation IOU is starting to plateau close to 1. From the mean IOU graph, it appears to be constant, a similar performance to the very first round iteration of the model. To be honest, I'm not sure why this is the case, and it would probably need time to investigate into how it is calculated in the Keras library. For now, I would ignore it and refer to the custom IOU function instead for a better metric measurement. From the accuracy graph, we can see that the accuracy of the model is quite low, and for the training accuracy, it dipped but increased slightly, while the validation accuracy fluctuated. To increase the accuracy, I can change the learning rate to 0.01 as per seen from the first round iteration analysis, but this would be at a cost to MSE, which I think is not advisable as MSE is a more important metric. Also, accuracy might not be a very good metric to assess the model performance. Lastly, from the MSE graph, we can see that the training MSE is gradually decreasing over time while the validation MSE is fluctuating around 0.014. I think that it is generally still fine as the MSE is quite low. The final test would be to select and run a few test DICOM images through the model for actual prediction. For the images with pneumonia detected above, I can see that the model predicts it generally quite well, although it is not the high IOU performance seen in the above IOU metric. At least the model is still able to detect the pneumonia area to a generally good accuracy. As for the images without pneumonia detected above though, I can see that the model performs poorly. Even though the image does not have pneumonia, the model will still predict a bounding box indicating pneumonia detected, albeit a significantly smaller and less clear bounding box area. This is also an area for improvement in order to make sure that the model works as expected, as having this issue will result in a high number of false positives. To conclude, the project's objective is to develop a model to detect pneumonia, and the model built so far would achieve this to a certain extent, but definitely can be improved further. With the current model, it can detect pneumonia with ease but with a certain degree of variance. The precise area needs to be further investigated by the healthcare specialists though, as the predicted area might be too large or not accurate enough. Also, there will be many false positives generated, as well as the current model predicts smaller pneumonia bounding boxes in images where there is no pneumonia detected. Hence, if there is immediate time constraint for model usage, the current model can serve as a first line of defense for screening the DICOM images. After the model predicts the bounding boxes, the healthcare specialist can prioritize those images predicted with a bigger bounding box area as patients with a higher probability of pneumonia detected. This will alleviate bottlenecks in reviewing such images in their triage process for determining priority of patients to administering the appropriate healthcare service to. Assuming there are no time constraints and in order to fully automate the process of detecting pneumonia, the model can and has to be further improved through the following points, which are: to improve the inputs to the custom generator by enhancing the code to handle for an image having multiple bounding boxes. The current setup only accepts one bounding box per image, and it may introduce an inherent bias. The next point would be to try different variants of the learning rate on the ADAM optimizer and consider perhaps even modifying the monitoring loss rate on model checkpoint, early stopping, and reduce LR on plateau to validate MSE instead. Thanks, and that's the end of the presentation. Hope that it is useful to you as a reference. So, what are your thoughts on it? Feel free to comment in the comment box down below. If you liked this video and would like to see more content of this nature, please be sure to like and subscribe as well. Thanks for watching, and until next time.